Okay, picture this. You've got a matchstick, right? Just this little sliver of wood with that funny-looking tip. You press it against the side of the box, give it a quick drag, and in that split second, you hear it. First, there's this little hiss, then a scratch, and then whoosh! This tiny dancing flame just springs into existence. You can feel the heat on your fingers, you see that bright orange light, but what in the world actually just happened? I mean, we see it all the time. We use it, we respect it, sometimes we're even afraid of it. But what is fire, really? When you look at a flame, what are you actually looking at? Is it a solid thing, like the match it came from? Well, no, you can't exactly grab it. Okay, so is it a liquid? It kind of flows and moves, but not really like water. Or maybe it's a gas. It's see-through, in a way. But that doesn't feel quite right either, so what is it? All right, to get to the bottom of this, we've got to rewind a little. We need to look at what was there before the flame showed up. Think of it like a recipe with some invisible ingredients. So before you even strike that match, two of our key players are already on the scene. First, you've got fuel. That's the chemicals on the match head and the wood itself. And second, you've got oxygen, which, is all around us in the air. But hang on a second. A log for a fireplace sits in oxygen-rich air all day, every day. So why doesn't it just, poof, catch fire on its own? What's the missing piece of the puzzle here? They're missing that final critical ingredient. They need a trigger. They need heat. That friction you create by striking the match, that's what provides just enough of an energy boost to kick the whole thing off. Okay, so we have our three ingredients: fuel, oxygen, and heat. Now, let's get into the really cool part, the incredible chemical reaction that happens when they all come together. That reaction has a name you've probably heard: combustion. And the two most important words there are rapid and self-sustaining. This isn't just a one-time thing. Once combustion starts, it actually creates the energy to keep itself going. It's a powerful idea. So here's how it plays out. That first spark of heat gives the fuel and oxygen molecules a little push, enough to get them over what scientists call an energy hill. Once they're over that hill, they react, and bam, they release a bunch of energy as more heat. And that new heat is now the push for the molecules right next to them, which then react and release more heat, and on it goes. It's a chain reaction, feeding itself as long as it has fuel and oxygen. And here's the big takeaway. That flame, that beautiful, flickering, dancing thing you're watching, it isn't really a thing at all. It's the place where that intense, super fast, self-sustaining reaction is happening. You are literally watching chemistry in action. So, we can finally answer our big question. What is a flame? It's a shape made of super hot gas and tiny glowing particles of soot, all created by combustion. It's not a solid, it's not a liquid, and it's not just a gas. It's a process. It's a visible transformation. This chemistry also explains why flames have different colors. That blue flame on your gas stove, that's a sign of a really hot, efficient, complete combustion. But the classic yellow flame of a candle, that's actually a bit cooler, and the yellow color comes from tiny particles of soot glowing hot before they've had a chance to completely burn up. The color is a dead giveaway for the kind of chemistry that's happening. Now, there's a really simple model that helps us understand and, more importantly, control fire. It's called the fire triangle, and honestly, it's the foundation of all fire safety. First up, we have fuel. This is pretty straightforward. It's just anything that can burn. Wood, paper, gas, you name it. It's the stuff the reaction needs to consume. The second side of our triangle is oxygen. This is the oxidizer, which for us is almost always just the air around us. No oxygen, no reaction. Simple as that. And the third side is heat. This is the energy that gets the party started, but it's also the energy that the reaction produces, which, as we know, is what keeps the whole thing going. And this is the genius of the triangle. To stop a fire, all you have to do is remove any one of those three sides. Break the triangle, and the fire goes out. When you pour water on a campfire, you're taking away the heat. When you put a lid on a grease fire, you're cutting off the oxygen. And when a wildfire stops at a road, it's because it ran out of fuel. Cool, smother, starve. It's all just about breaking that triangle. So let's look at how this one chemical process, combustion, can be both one of our greatest allies and one of our most dangerous enemies. Think about it. On one hand, you've got a birthday candle.
It's a controlled fire. The fuel is limited to just the wick and the wax. It's manageable. It's helpful. But on the other hand, a wildfire is the exact same chemistry. The only difference? It has an enormous uncontrolled supply of fuel. One is a friend, the other is a foe, and the only thing separating them is control over that fire triangle.
So the next time you see a flame, whether it's a tiny flicker from a lighter or a big roaring bonfire, just take a second and remember what you're really looking at. You're not seeing a thing. You're watching a process. You're witnessing chemistry made visible. It's this beautiful, powerful reaction that has shaped our world. It's chemistry that you can actually see.